Okay, so can everyone get their piece of paper? Okay. And I want you to make one fold. One fold, Joe. One fold.
Hang on.
Not your hat. Do it later. I want to see it later. Can you do this first?
Yeah.
One fold. One fold. Okay.
In half.
Yeah. So we're going to say, it doesn't matter which way, we're going to say that the area of this whole piece of paper is 1. Okay. So when I made one fold,
You put it into half.
yeah. So when I made, when I made one fold, how many parts are there?
2.
2. Okay. So there's 2 parts, and what's the area of each part?
Half.
Right.
Third
Because if
part.
the area of the whole thing is 1, we said the area of one part is half.
my
Once I've
God.
folded it like this. Can you make another fold for me now? Make another fold. Doesn't matter which way again.
I don't know, okay.
I'll just grab a piece. Grab that one.
This is really easy, so why are we doing this?
It's good. It's good. That's easy. So how many parts do you have now when you unfold it?
4.
4 parts? And why is the area of each part a quarter? 4 parts, right?
I want to do this, mate.
Keep going for me, keep going.
I want to do this.
One more.
I want to do Pepper Hat, man. Now there's 8.
Okay, and what's the area of each part?
1.
And you don't have to keep doing it for me, but you know that there's a pattern emerging. What's the pattern in this case?
It doubles.
Yeah, that's true. So as the number of folds you do, the number of parts double. But what's the relationship between the number of parts and the area of each part?
I don't know how you'd say it.
Okay, yeah, well, what are you thinking there?
Obviously, it's just 1 over the
Right.
number of parts.
So you see the number on the number of each parts is the denominator of the area of each part. Is that what you're trying to say?
Yeah.
Yeah, good. And that's exactly what I want you to see. We can actually express that mathematically, okay? Because visually it's really easy to see, but mathematically we can define that as y is equal to 1 over x. Y is equal to 1 over x. Okay. Now you just want to be really careful with what's your variables here, because I always get this confused. But the number of parts in this case is y, and the area of each part is x. Okay, so let's just double check that works. I'm saying that 2 is equal to 1 over half, okay? And that works out because when you take the reciprocal, you get 2 is equal to 2. So that's a pattern that's emerging. You've got y equals to 1 over x. And that's the whole idea behind inverse variation. It's as one thing is increasing, so the number of parts is increasing, the area of each part is what's happening to it.
Decreasing.
It's getting smaller and smaller. We had a couple of examples of this. I gave you one example where, remember when you were digging? Right, so what did I say? Do you remember that example?
You dug, but the bigger the hole was, the more dirt there would be.
No,
Further went down, sorry.
not quite like
the
that.
more people that dig, the less time it's going to take.
Right, yeah, so there's 2 variables. I'm not sure where you're going with the whole one, but I was more thinking about the amount of diggers.
Something.
As you increase the diggers, what's happening to the time? The time gets less. Okay, so increase people, decrease time. There's a lot of other relationships like this. For example, the faster you are, what's happening to the time of your journey?
The slower it takes.
So as I go faster, if I'm going like 50 km, it's going to 100
Your time decreases.
time decreases, so time goes down. What about, do you guys know, think about when you're home on your Wi-Fi, when there's like a lot of people trying to use it.
It's slower.
Right,
It
yeah,
dies.
so the number of users on a Wi-Fi network, that's going to reduce the speed that you get. Okay, so we've got all these different inverse relationships happening.